Thanks for the introduction, and also thanks to the organizers for the invitation to present here today. I'm a PhD student in the group of Lieven van der Sijpen in QTech at the Delft University of Technology. And in this talk, I first want to introduce you a bit to silicon spin qubits, and then I will present two experiments we did in our group on gate fidelities and spatial noise correlations in such a sample. And then at the end of the talk, I will present some work, some recent work that we did on developing a design for a sparse spin-qubit array that is designed to sustain the surface code. So usually our experiments, we start with a two-dimensional electron gas that in this case is confined in a heterostructure at the interface between gallium arsenide and aluminium gallium arsenide. And then by tuning voltages that we apply to these metallic surface gates, we locally deplete the 2-deck, and that way we confine single electrons in little islands. And by tuning these voltage, we can accurately control the number of electrons in these quantum dots. And then we apply an external magnetic field that splits the spin states of these electrons due to the Zeeman effect, and we then use the spin up and spin down states to define a qubit. For decades, gallium arsenide has been the workhorse material to perform quantum dot and spin qubit experiments because of its excellent material quality. However, in gallium arsenide, all nuclei possess a spin, and that drastically limits the coherence of the electron spin due to the hyperfine interaction. Now, in natural silicon, only 5% of the nuclei carry a spin, and the coherence of the electron spin is way better. It leads to a 2 orders of magnitude increase of the spin coherence. But we can even do better by isotopically purifying silicon, and thereby reducing the concentration of silicon-29 nuclei in the sample. That way we can effectively eliminate the hyperfine interaction as source of decoherence, and this improves the coherence times by another 1 or 2 orders of magnitude. In addition to this small hyperfine interaction, also the spin orbit coupling in silicon is relatively weak. And there is decades of experience with silicon in conventional CMOS fabrication. And that's exactly the thing we want to leverage in spin qubit fabrication and on-chip integration of our qubits with classical control electronics. And that's an important reason why we at QTech work so closely together with Intel, but also while other companies have similar projects. So in the last few years, we have seen quite quick progress in silicon spin qubits with long coherence times, high fidelity single qubit gates, 2-qubit gates, and also quantum algorithms. Small scale quantum algorithms have been demonstrated, and also first spin-photon coupling and later long-distance spin-spin coupling has been shown in silicon devices. So these experiments, the quantum algorithms experiments, were done by a few of my colleagues in Delft. It's a silicon-silicon germanium sample with natural silicon isotope composition that is fabricated by the group of Mark Erickson in Wisconsin. And my former colleague, Tom Watson, was able to tune 2 spin qubits in this device with coherence times of 1 and 0.6 microseconds. And he demonstrated that he could program this 2-qubit quantum processor at will to perform both the Deutsch-Jozsa and the Grover algorithms. And now having a device at this stage opens up the possibilities for quite a lot of interesting experiments. And I will present the results of 2 of the experiments we did, starting with assessing gate fidelities of both single and 2-qubit gates in this device. So with the 2 qubits, we first start with single-qubit randomized benchmarking, and then there are 2 versions of this experiment that we can do. We can apply random sequences to only one of the qubits, while we leave the other qubit idle. But we can also apply random sequences of Cliffords to both qubits simultaneously, which of course is a more realistic scenario in a full-scale quantum computer. So we performed both these experiments, and for the case of individual driving, we found gate fidelities of 99.2 and 98.9%. And for simultaneous driving, we find 98.8 and 96.9%. So we see that by driving the qubits simultaneously, the fidelities drop a bit, and especially for qubit 2. We also observe that this effect still is the case if we apply the drive to the other qubit off-resonantly. So from that we conclude that it's the microwaves themselves that cause this effect, and not the operations on the qubit that cause this. And later I will argue that this effect comes from some form of classical crosstalk or leakage to another state. Then after having characterized the single qubit gates, we want to characterize the 2-qubit gates. And in our case, that's the C-phase gate. The traditional approach to this would be to first perform full 2-qubit standard randomized benchmarking, and then interleave this C-phase gate in this sequence after every random Clifford, random 2-qubit Clifford. By comparing the decay curves of these 2 experiments, we can then extract the fidelity of just the C-phase gate. So we performed the reference experiment and extract an average Clifford fidelity of 82.1%. But what we also see here is that the curve actually saturates pretty quickly, and this makes it completely unfeasible to perform this experiment. The reason for this is that the compilation of 2-qubit gates is quite complicated, which makes that the length that such a sequence takes, one 2-qubit Clifford on average takes 1.5 C-phase gate and 8.25 single-qubit gates. So the length that such a sequence takes, combined with the lower fidelity of the 2-qubit gate, makes that this curve saturates quickly, and that we can't really perform this experiment. But let's take one step back maybe. What we actually are interested in is just this C-phase gate. And we don't care so much about these blocks C1, C2, etc. So now the idea is, can we maybe, instead of interleaving the C-phase gate in full 2-qubit sequence, can we interleave it in a sequence with only single-qubit gates as a reference? This would have 2 advantages. First, it actually becomes feasible to do this experiment because the compilation is way easier, and so the curve doesn't saturate that quickly. And also, the extracted fidelity of the C-phase gate, or the bounds on the fidelity extracted from this experiment, are tighter because of the single-qubit gates giving a higher fidelity reference sequence. But the question is this a valid experiment to perform, and is the fidelity you would extract this way meaningful in any way? And that's exactly the question my colleague Xiao Xui asked himself. The answer is yes, but it's not simply yes. So let's have a quick look at some background. In single-qubit randomized benchmarking, it's relatively simple. In performing this random sequence of Cliffords, we send the qubit to one single noise channel that causes the infidelity of the gates. If we now perform full two-qubit randomized benchmarking and apply the random sequence of two-qubit Cliffords, we send two qubits to one big noise channel together. But if we now perform simultaneous randomized benchmarking on the two qubits, what we actually do is we send these two qubits through isolated noise channels that do not mix because the single-qubit gate, the two-qubit gate is missing. These three noise channels correspond to different subspaces of the full Hilbert space that are isolated from each other. And this way you only consider a subgroup and you miss part of the noise mapping of these different sigmas onto each other. So then our theory colleagues in Delft, Jonas Helsen and Stephanie Wehner, came up with the idea of adding an extra random gate in front of the sequence of random Cliffords. And this extra gate is sampled from what's called the character group, and in our case we use the two-qubit Pauli group as the character group. And in addition to averaging over the random sequence of Cliffords, you now also average over this extra Pauli gate. And in doing that, you apply a weight that by, let me see. You weight it by what in representation theory is called the character function. And that's where, well, the name character randomized benchmarking comes from. And what these Pauli gates essentially sort of do is they flip the sign of a specific noise channel and thereby it makes it possible to extract information on these isolated noise channels. Knowing that, we can then use that as a reference to interleave the C-phase gate in the sequence and extract the fidelity of the C-phase gate. To make this a bit more explicit, in simultaneous randomized benchmarking, we in total have 15 noise channels of 3 different types. One for qubit 1, one for qubit 2, and one for qubit 1 and qubit 2 combined, and the later here is sort of the parity decay. And all these 3 types of noise channels are now reflected in the recovery probability of the final state that is a combination of 3 exponential decays. In character randomized benchmarking, we add this pair of random Pauli operators to both qubits, and there in total are 16 two-qubit Pauli operators. Those we combine in the probabilities P00, 01, 10, and 11 to obtain the 00 state after starting from the 00, 01, 10, and 11 state. This way, each of these 4 contains 4 of these Pauli operators. Then we make linear combinations of these 4 probabilities according to their character, and that way we isolate the 3 different, the 3 isolated noise channels. We can fit those to a single exponential decay to extract the depolarizing parameters for the isolated noise channels. And then finally, we can derive the full depolarizing parameter by combining these and applying the proper weight. So we first perform the reference character randomized benchmarking experiment that consists of a random Pauli on both qubits followed by a random sequence of Cliffords, single-qubit Cliffords to both qubits. And then we can add a C-phase gate after every 2-qubit Pauli pair, 2-qubit Clifford pair in the interleaved experiment. So here I show the data for both these experiments. For the reference experiment, we extract a 2-qubit, we extract a single qubit gate fidelity in 2-qubit space of 92%. And for the interleaved experiment, we directly see that the three curves are closer together. And the reason for this is that we now do have the 2-qubit gate that directly contributes to the decay of these three channels, but it also mixes the channel, the three channels. And that from that, we then can extract the depolarizing parameters for the three channels, and by comparing them with the reference experiment, we can extract a 2-qubit gate fidelity of 92%. But there is even more information in this reference character randomized benchmarking experiment that you will not get from standard randomized benchmarking. And in this case, it is that we can extract information on the correlations in qubit errors on those 2 qubits. And the fact that this number is essentially 0 tells us that there are no quantum correlations in those errors between the qubits. And that's actually what we would expect, because our qubits have a difference of 1.3 gigahertz, so we have perfect addressability in the sample. There is negligible residual exchange coupling between the 2 qubits in these experiments, and we also rule out the AC Stark effect. And this is the reason that I mentioned earlier that this must have a classical origin. We have some indications that it might be a heating effect that causes this, but more further studies are needed to confirm that. To summarize this part on randomized benchmarking, we performed the first complete characterization of single and 2-qubit gate fidelities in a silicon spin qubit sample. We extracted single qubit gate fidelities of 99.2 and 98.8% for individual driving, and we see that they drop slightly to 97, 98% for simultaneous driving. Together with our theory collaborators, we developed character randomized benchmarking and used that to extract the C-phase fidelity of 92%. And we concluded that the errors that we see in our sample are independent errors. And those independent errors that we observe in character randomized benchmarking naturally bring me to the next topic, a study on spatial noise correlations in the exact same device. And this is an interesting topic because large-scale quantum computers will have to rely on quantum error correction to deal with the inevitable errors coming from the environment and imperfect control pulses. Most of the quantum error correction schemes assume negligible correlations in those qubit errors, and also the 1% threshold for the surface code that's commonly quoted is derived under this assumption. So it's important to know to what extent the noise finally causing these errors is correlated. Now, thinking of global fluctuations in our sample that have a similar effect on 2 qubits that are only separated by 100 nanometer or so, it seems reasonable to expect that the noise is correlated to a large extent. So don't we expect the noise to be correlated? And this is our main reason to study noise properties. Other reasons are that knowing about the properties of the noise make it possible to exploit decoherence-free subspaces, and it potentially allows to identify noise sources and maybe eliminate them. So in this work, we are looking at spatial correlations in a noise acting on 2 qubits in the exact same device That, as I said, was used for the two-qubit algorithm experiment and also for the randomized benchmarking experiment. Schematically, we have two qubits in an external magnetic field. But what I didn't mention yet is that in addition to this external magnetic field, there is a contribution to the total magnetic field coming from micromagnets on top of our sample. And the result is a difference in Zeeman splitting between the two qubits. And that is reflected in this energy diagram here. Now, for the case of correlated noise, the fluctuations of these energies, of the Zeeman energies, are the same. And that means that the sum of those energies does fluctuate, while their difference will remain constant. This means that correlated noise does have an effect on a parallel Bell state, but it leaves the anti-parallel Bell states unaffected. On the other hand, perfectly anti-correlated noise has an opposite effect on the two Zeeman energies, meaning that their sum remains constant while the difference does fluctuate. So anti-correlated noise does have an effect on the anti-parallel Bell states, but not on parallel Bell states. Yes, that's what I mentioned. So then first, moving to experiments, we essentially do Ramsey-type experiments with two qubit states. Starting from the 0-0 state, we show in these diagrams that we prepare an anti-parallel or a parallel Bell state. Then we wait for some time and reverse the sequence to go back to the 0-0 state. And then we measure the single spin probabilities, convert them to two spin probabilities, and fit a Gaussian decay, as shown here. Repeating these measurements, we see a trend towards longer T2 star values for the anti-parallel Bell states, which reveal sparsely correlated noise. But contrary to what one might expect, these correlations are rather small, because for perfectly correlated noise, the T2 star for the anti-parallel Bell state would be infinite. And we have even observed smaller correlations. And all this is good news for quantum error correction, because it seems to justify this assumption of little correlations in qubit errors. To verify that our method is correct, we introduce artificial dephasing in our experiments. We do this by applying z-rotations to the qubits in software, and then measure the decay time. And these z-rotations are either correlated or anti-correlated. The solid lines here are theoretical predictions, and we indeed sort of see the trend that anti-correlated noise does have an effect on the anti-parallel state, but not on the parallel state, and the opposite for the correlated noise. And this validates our measurement protocol. To now gain some insight in the frequency dependence of the spatial correlations that we observe in the noise, we perform measurements analogous to Hahn echo experiments. What we do is we apply pi pulses to both qubits, halfway the waiting time, and then we observe a factor of 4 to 5 increase in the coherence times. But there is no systematic difference in the coherence times for the anti-parallel and the parallel Bell state. So this means that there are no detectable spatial correlations at higher frequencies. To get some better understanding, we used a simple model to derive theoretical expressions for the T2 stars of the two states. And here, sigma 1 and sigma 2 are the standard deviations of the noise acting on qubit 1 and qubit 2 respectively, and rho is a correlation factor. Positive rho indicates correlations, while negative rho indicates anti-correlations. Now this figure shows the effect of the noise amplitude and the correlation factor on the coherence time of the antiparallel Bell state. At rho is 1, because the sigma 1 and sigma 2 are the same, at rho is 1, this antiparallel Bell state is a true decoherence-free subspace, and the coherence time of the antiparallel Bell state is unaffected by this noise. It remains constant irrespective of the noise amplitude. With decreasing rho, the correlations get smaller and eventually become anti-correlations, and the coherence time reduces. At rho is -1, the noise is fully anti-correlated, and the coherence time of this antiparallel Bell state is only 1/4 of the single qubit coherence times. Then, looking at the effect of sigma 1 and sigma 2 individually, we see that even for rho is 1, there is only a true decoherence-free subspace for symmetric noise where sigma 1 and sigma 2 are the same. So these two figures highlight the important effect of both asymmetry in the noise amplitude on the 2 qubits and the correlation factor on the 2 qubit coherence. So, as I mentioned, when we started this project, we essentially expected to observe mostly correlated noise based on the idea that we have 2 qubits that are really close together, only 100 nanometers or so, and that global fluctuations would have a similar effect on those 2 qubits. The theoretical model I just showed you shows the importance of asymmetry in the noise amplitude on the 2 qubits. So let's see whether we can use this to maybe also understand why we observe mostly uncorrelated noise in the device. The combined effect of multiple independent noise sources that all produce correlated noise on the 2 qubits with the same relative amplitude will simply produce correlated noise with that relative amplitude. But if now this relative amplitude becomes random, the noise quickly is indistinguishable from uncorrelated noise. And as an extreme, symmetric correlated plus anti-correlated noise with equal amplitude is completely equivalent to uncorrelated noise. And these effects are described by this expression. And from this, we think of a combination of multiple independent charge fluctuators as a likely scenario for the small correlations that we observe. As an example, we simulated the combined effect of 3 asymmetric correlated noise sources, 3 independent asymmetric correlated noise sources, and if we now look at the distributions of the fluctuations of the difference and sum frequencies of the 2 qubits, we still do see some correlations, but it's far from perfectly correlated. And based on this, as I just already said, we think of multiple distant charge fluctuators with asymmetric coupling to the 2 qubits as a likely scenario, and this also agrees with our theoretical analysis. And based on our further knowledge of the device, this asymmetric coupling seems indeed to be the case. To summarize also this part on noise correlations, we observe only modest spatial noise correlations at low frequencies. At higher frequencies, the correlations seem to be absent. And a scenario of multiple asymmetric anti-correlated or correlated noise sources is in agreement with the data and our understanding of this device. I also want to highlight our insights of the importance of the asymmetric coupling of noise sources And we expect that the optimization of quantum error correction protocols and the design of qubit devices will go together. Then in the remainder of this talk, I will show you some recent work on a sparse spin-qubit array that we designed to sustain the surface with, or that we designed with the surface code in mind. Our design starts from a 22 by 33 millimeter die, and part of that is the quantum plane and that's where the qubits reside in a two-dimensional array. This quantum plane contains m squared modules, and each module is n squared unit cells, and each unit cell again, or then contains 4 qubits. To be able to integrate local sample and hold circuits, we set the qubit pitch to 12 micron, and then with a total number of about 1 million qubits, for example, the total area of this quantum plane would be on the order of 150 square millimeters, leaving plenty of space on the die that can be used to further reduce the number of off-chip connections. A unit cell is the smallest operational unit in our design. It contains 2 data and 2 ancilla qubits that reside on the vertices of our array, and they are connected via horizontal and vertical shuttling channels. To perform operations on the qubits, the electrons are shuttled from the vertices to the operation regions, halfway the shuttling channels, and there the operations are performed. The local sample and hold circuits that I just mentioned allow for individual DC biasing of all the gates in our array to offset any inhomogeneity in the potential landscape in our sample or in the array. And from there on, we then can treat the full array as completely homogeneous and reuse all control signals across the entire array. And that allows for a very efficient scaling of the number of control lines to sustain the surface code. So yes, we designed this array with the surface code in mind. Here we again have the unit cell with 2 data qubits in blue and 2 ancilla qubits in red. And these are then the cycles for the X ancilla and the Z ancilla with all single qubit and 2-qubit interactions with the 4 neighboring qubits. Now combining these 2 cycles, we get a single surface code cycle for a unit cell, where the dashed lines indicate a 2-qubit interaction with a qubit in one of the neighboring unit cells. As an example, in step 1, we shuttle both the X and the Z ancilla from their crossing to an interaction region to perform a Hadamard gate on both of these qubits. And this also directly shows why step 1 and step 2 need to be separate, because the single qubit gate on data qubit 1 has to be performed at the same location as where we perform the single qubit gate for the Z ancilla. In, for example, step 3, we see 2-qubit interaction where data qubit 2 and the Z ancilla are shuttled to the same interaction region to perform a 2-qubit interaction between these 2 qubits. And then to perform logical operations on top of just the surface code cycle, our scheme relies on lattice surgery. And we do that by not shuttling the data qubits over to this interaction region. So the ancilla qubits will just move to their respective interaction region, but the data qubits stay at the vertex, and there is no 2-qubit interaction here. To prevent the data qubits from actually being shuttled over to this interaction region, we use crossbar addressing. And when we now address a set of horizontal and vertical lines, the qubits at their crossings are prevented from being shuttled, and that way we create defects in the service code lattice. We can this way create rectangular defects of any size and aspect ratio, and we're able to move them around by changing the lines that we activate. With that, I want to summarize my talk. I showed the first complete characterization of single and two-qubit gates in silicon spin qubits. We've observed minor spatial correlations in the noise acting on two qubits, on those two qubits, and I've showed you our recent work on a design for a sparse spin qubit array with the service code in mind. With that, I want to thank all members of my group, and of course you for your attention, and I'm happy to take any questions.
I have a couple questions. One is, do you use the same magnetic field for all of the qubits? Well, in the experiments you only had two, and it had the same magnetic field.
Are you referring to the experiments I showed, or to the array part at the end?
Well, actually, I'm interested in the array, but so yeah, answer whatever you will.
Well, so in the experiments, yes, the qubits are really close together, so they are in the same external magnetic field, but they do have a different Zeeman splitting as a result of those micromagnets on top of the sample. So effectively, they do have a different total magnetic field acting on them. In the array I just showed you, we envision one global magnetic field, and I didn't show that here, but we do require micromagnets again for single qubit operations, but those are only here. So while the qubits are here, on the vertices, the magnetic field for all qubits is the same.
Also, second question is, when you shuttle the qubits back and forth, it's not very big distance in this lattice. Will there be spin orbit rotations due to the motion of the qubits?
Well, that's something that we need to look into. That's absolutely true. In silicon, one of the advantages is that spin-orbit coupling is relatively weak to, for example, gallium arsenide. But it's definitely something we need to consider. Yeah.
Hi, thanks for the great talk. I was wondering about the measurement errors. How well characterized are the measurement errors, and how do they relate to the two-qubit?
In the experiments I just described, I think we didn't again characterize the measurement errors, but what I remember from the quantum algorithm experiments that I mentioned briefly in the beginning, the readout fidelity is on the order of 80%.
Okay, so that sounds like that would actually dominate if you kind of consider one qubit gates, two qubit gates, and measurement, single qubit measurements, then the worst errors would be the measurement errors, is that right?
That's indeed true. The measurement is for now the weak point, but in the errors I show, or I quote, those are not taken into account because randomized benchmarking is designed to, of course, not take them.
Okay, I think there was a question.
When you did the characterization, do you learn anything? I don't think you said it in the talk about the nature of the type of errors. So you said there weren't any correlations, but do you have an idea of whether they're bit flip or phase flip type errors in your CC gate?
We don't know directly, but given that our T1, if I go back all the way to the start, that's probably easier here. The T1 for our qubits is really long compared to both the T2 time and the operation time. This takes long. Almost there. Oh. Yes. So for qubit 1, the T1 is longer than we can measure, and for the for qubit 2, it's still way longer than both T2 and any relevant time for the operations we do. So in our sample, pure dephasing dominates.
Thank you.
Okay, in the back.
Probably just yell if you want to stay.
It should be on the recording, so please.
Okie doke. Thanks for the great talk. So apologies if a couple of these things were in your talk and I missed them. But I wonder if you could say a bit more about your proposed surface code architecture. So I was interested in the scale of it. So what would a single unit of it look like? I was interested in how much global control you would aim to use, and so how much homogeneity that you need in your fabricated device. I guess those are the two key things. Also, I guess the cycle time.
Yeah.
So in other words, the time for one complete stabilizer evaluation.
Well, first of all, let me stress that this, of course, is something in our mind. It's not fabricated yet. So, I now forgot half of your question. I'm sorry.
So I guess the typical scale. I realize that it's a back of the envelope type, But what sort of is it a micron? Is it 10 microns? Is it 10 nanometers? What's the scale of one plaquette?
Yeah. So
what's the cycle time of a plaquette?
well, the scale of the plaquette, so the physical size, what we have in mind now is on the order of 12 micron from vertex to vertex. So the qubit pitch is 12 micron, and that's only determined by the size that we actually need in the open area to implement those sample and hold circuits. In how long such a cycle takes, what I can say for now is that a typical gate time in silicon spin qubits for a single qubit gate is, say, on the order of 100, 200 nanoseconds, and our 2-qubit gates is also on the order of 100 nanoseconds. So that would give, say, on the order of 1-2 microseconds quick calculation for the operations, but the readout is by far the longest in our type of devices, more on the order of milliseconds in the way we do the measurements now. So there are proposals to increase that or to reduce the measurement time, also to on the order of microseconds. So then the full cycle would be on the order of 10-100 microseconds, I believe. But this is just quick calculation, and that's, say, the next step that we need to look into further.
Thank you very much.
Okay, maybe one quick last question.
To my knowledge, I might be wrong. So I think it's relatively, hard to fabricate two identical quantum dots in general, right?
Yeah.
So like, it doesn't really show in the 2-qubit case, but like in the general case, so we're doing like a surface code which requires like probably tens or thousands of qubits. Like, is there a way to overcome that?
Yeah. So first, on actually making reproducible quantum dots, that's one of the reasons that. What I mentioned in the start of my talk, we collaborate with Intel, but also other companies are involved. We hope that their experience with conventional CMOS fabrication helps us in making more reproducible and reliable spin qubit devices. That's on the one side. On the other side, we probably have to face that qubits will have their own identity. And that's exactly why we think of this idea, where we have a sparse array and we implement the possibility to locally correct for exactly those differences that you mentioned. There are other proposals that I didn't mention now, where the qubits are way closer together, but that comes with quite stringent requirements on the homogeneity of the array. And exactly that's what we want to tackle with this proposal.
Thanks.
Okay, let's thank Jelmer again for this beautiful talk and all the speakers of the afternoon.